Welcome to the sleepy universe. If you enjoy calm explorations of strange and beautiful science, consider liking this video and subscribing to the channel. And while you're here, let us know where in the world you're watching from. It's one of those quiet facts that makes the universe feel a little bit smaller. Somewhere in the universe, right now, there is a place where space itself bends so severely that even light cannot find its way back out. A place where the very geometry of existence has folded over on itself, where the direction we call forward in time and the direction we call toward the center become, in the most mathematically rigorous sense, the same direction. A place that holds more compressed mass than entire stellar nurseries, packed into a region smaller than a city, or in some cases, smaller than a single atom. A place that sits in silence, not the peaceful silence of an empty room, but the absolute silence of a boundary beyond which no signal, no message, no photon of light has ever returned to tell us what lies inside. That place is a black hole, and tonight we are going to ask one of the most quietly extraordinary questions in all of science. Not what is a black hole in the textbook sense, not a recitation of definitions and distances, instead something stranger, more personal and more unsettling. We are going to ask, as calmly and as carefully as the physics allows, what would it actually be like to fall into one? This is not a simple question with a single answer. It is a question that splits almost immediately into two completely different stories, depending on where you happen to be standing. If you are standing far away, watching someone fall in, you would witness something deeply counterintuitive, something that seems to contradict the very premise of the question. If you are the person falling, you would experience something almost equally strange, but in an entirely different direction. These two accounts, as we will see, are not in conflict with each other. They are both correct. They are both genuine descriptions of what happens. And the reason two observers can have such different experiences of the same event is one of the most important things that general relativity has to tell us about the nature of time itself. The answers involve physics that was worked out by a soldier writing equations in a trench during the First World War. They involve a mathematician in New Zealand finding a solution in 1963 that half a century of brilliant minds had failed to crack. They involve a brief and extraordinary collaboration between quantum mechanics and gravity that produces a radiation so faint it has never been detected but is almost certainly real. And they involve a boundary so philosophically unsettling that the physicists who study it for a living have spent decades arguing about what it actually means. This is not a video about breaking the laws of physics or finding ways around them. The laws win. They always win. This is a quiet walk through what those laws actually say, taken slowly, with enough time to let the strangeness of it settle into something that feels, if not ordinary, at least honestly understood. The kinds of black holes. Before we can fall anywhere, we need to know what we are falling into. Not all black holes are the same. They come in different sizes, formed by different processes, and the difference between them is not just a matter of scale. It changes the entire character of the journey. The smallest and most common are called stellar mass black holes. These are the remnants of massive stars, typically those with initial masses somewhere between about 20 and several hundred times the mass of our own Sun. When such a star exhausts its nuclear fuel after millions of years of burning, the outward pressure that has held it up against its own gravity disappears. What follows is a catastrophic collapse so sudden and so violent that it shakes the fabric of space-time itself, sending gravitational waves rippling outward across the cosmos. The outer layers of the star are blasted away in a supernova explosion visible across entire galaxies. The inner core, however, collapses inward without anything left to stop it. The result is a stellar corpse with a mass typically between 5 and roughly 50 times that of the Sun, but with all of that mass compressed into a volume smaller than a single atom. The gravitational field around this object is so extreme that at a certain distance, called the Schwarzschild radius, named after the German physicist Karl Schwarzschild, who calculated it in 1916 while serving on the Eastern Front of World War I, the escape velocity reaches exactly the speed of light. Any closer and nothing can get out. That boundary is the event horizon. For a black hole with the mass of our Sun, the Schwarzschild radius is approximately 3 kilometers or about 1.9 miles. The Sun itself has a radius of roughly 696,000 kilometers. So a solar mass black hole would squeeze all of that mass into a sphere the size of a small town. The density involved is not a number that connects to any intuition we have built from ordinary experience. A single teaspoon of matter at the density of the singularity would contain more mass than all of the observable universe. That is not a meaningful comparison to hold in the mind. It is simply a statement about the limits of physical intuition applied beyond its domain. The formation of stellar mass black holes is not uniform. Stars of different initial masses take different paths through their deaths. A star of about 8 to 20 solar masses will typically end its life as a neutron star rather than a black hole. The collapse is halted by the pressure of tightly packed neutrons before the event horizon forms. Only above a certain mass threshold does the collapse continue all the way to a black hole. The exact threshold depends on the composition and evolutionary history of the star, and there is a current active area of research into whether there might be a mass gap between the heaviest neutron stars and the lightest black holes, or whether objects in between these categories exist. The LIGO gravitational wave detector has detected mergers of compact objects whose masses fall in ranges that have challenged simple classifications, suggesting that the story of stellar remnant formation is more complex and varied than the classic picture. At the other end of the scale are the supermassive black holes, and these are the ones that sit at the hearts of most large galaxies, including our own Milky Way. The black hole at the center of our galaxy is called Sagittarius A star, and it contains approximately 4.3 million times the mass of the Sun. Its Schwarzschild radius is about 12 million kilometers, roughly the distance between the Sun and the planet Mercury. In April 2022, the Event Horizon Telescope collaboration, a network of radio observatories spread across the entire planet, working in coordination to function as a single Earth-sized instrument, released the first actual image of Sagittarius A star's event horizon shadow, confirming what decades of stellar orbital observations had already strongly suggested. The stars near the galactic center orbit this invisible object at enormous speeds, some reaching velocities of up to 17 million miles per hour as they swing through their closest approaches. The star S2, the most observed of these, completes one full orbit of Sagittarius A star in approximately 15.9 years. Tracking its elliptical orbit over more than a decade allowed astronomers Reinhard Genzel and Andrea Ghez, who shared the 2020 Nobel Prize in Physics for this work, to measure the mass of the central object with exquisite precision and establish beyond reasonable doubt that it is a supermassive black hole. Beyond Sagittarius A star lies a more extreme example. The black hole at the center of the galaxy, Messier 87, located approximately 55 million light-years from Earth, contains roughly 6.5 billion solar masses. Its event horizon shadow spans a distance so vast that the shadow alone, were it placed at the center of our solar system, would extend well beyond the orbit of Neptune. This is the object that was first photographed by the Event Horizon Telescope in April 2019, producing the now iconic orange glowing ring of superheated gas against the deep void of the shadow. The image required years of data processing by a team of more than 200 researchers working across dozens of institutions. The appearance of the M87 black hole in that image was strikingly consistent with the predictions of general relativity, a bright, slightly asymmetric ring of emission. The asymmetry caused by the Doppler beaming of the rotating accretion disk surrounding a dark central region whose size matched the predicted event horizon shadow. At the extreme end of what has been measured sits a quasar called TON 618, located more than 10 billion light-years from Earth. The light we receive from it was emitted when the universe was less than a quarter of its current age. The black hole powering it contains more than 66 billion solar masses. Its event horizon shadow is so enormous that even light, traveling at approximately 300,000 kilometers per second, would take more than 2 weeks to cross it. There is also a hypothetical intermediate class containing hundreds to hundreds of thousands of solar masses, whose existence is suspected but harder to confirm observationally. Intermediate mass black holes may form from the mergers of stellar mass black holes, or from the collapse of very massive stars in the early universe, or through other mechanisms not yet fully understood. Their detection has been challenging, but several candidates have been identified through gravitational wave observations and through the properties of globular clusters, where dynamical evidence suggests the presence of a central massive object, too heavy to be a neutron star, and too light to be a supermassive black hole. Beyond even the supermassive classification, there are what some researchers call ultramassive black holes, with masses approaching or exceeding 40 billion solar masses, though confirmed examples remain rare. Why does size matter for our journey? Because the experience of falling changes dramatically depending on which type of black hole you are approaching, and the difference has everything to do with a concept called tidal forces. The force that unravels everything. To understand tidal forces, start somewhere familiar. The ocean tides on Earth are caused by the Moon's gravity pulling slightly harder on the side of the Earth facing the Moon than on the far side. The difference in gravitational pull across the diameter of the Earth is small, but it is enough to stretch the ocean slightly in the direction of the Moon, raising the water level on both the near and far sides simultaneously. This difference in gravitational pull across an extended object is a tidal force, and it is the same fundamental physics that makes falling into a black hole either an immediate catastrophe or a surprisingly unremarkable initial experience, depending entirely on the black hole's mass. The mechanism is straightforward in outline. Gravity follows an inverse square law. The force is stronger when you are closer and weaker when you are farther away. Any extended object, a star, a planet, a human body, has parts at different distances from the gravitating source. The near side feels a stronger pull than the far side. The difference in pull tends to stretch the object in the direction pointing toward the gravitating source and compress it in the perpendicular directions, because the near edge is accelerating faster than the center and the far edge is accelerating slower. But all three parts are part of the same object and can only partially compensate for these different accelerations through their structural strength. When you fall toward a black hole, feet first, the gravitational pull on your feet is stronger than the pull on your head because your feet are closer to the black hole. This difference stretches you along the direction of motion. At the same time, because everything about you is falling toward a single center point, the gravitational pull on your left side and your right side both angle slightly inward toward the center. This compresses you sideways. You are being stretched lengthwise while being squeezed widthwise simultaneously. The process was popularized by Stephen Hawking, who described a fictional astronaut being stretched like spaghetti, and the name stuck. Physicists call it spaghettification, though in more formal contexts it is sometimes called the noodle effect. The tidal force across an object of a certain length depends on three things: the length of the object, the mass of the black hole, and critically the distance from the black hole cubed. The cube relationship means that tidal forces grow extremely rapidly as you move closer. If you halve your distance from a black hole, the tidal force does not merely double, it increases by a factor of 8. Halve it again, and the tidal force increases by another factor of 8. This rapid escalation is why tidal forces go from unnoticeable to catastrophic over a relatively short distance near a sufficiently compact object. But the mass of the black hole cuts the other way in an important manner. For a larger mass, the event horizon sits farther out in physical distance, and the gravitational gradient across a human body at that distance is actually weaker, not stronger. The Schwarzschild radius scales linearly with mass. Double the mass, double the radius. The tidal force at the horizon scales inversely with mass squared, so doubling the mass quadruples the Schwarzschild radius, but reduces the tidal force at the horizon by a factor of 4. The result is that the larger the black hole, the gentler the tidal forces at its event horizon. For a stellar mass black hole with 5 times the Sun's mass, the event horizon sits only about 15 kilometers from the singularity. The gravitational gradient at that distance is ferocious. A rough calculation, drawing on historical military records for the force required to pull a human body apart, which sits around 9,000 newtons, suggests that a person approaching such a black hole would be torn apart at a distance of about 700 kilometers from the event horizon. That is hundreds of kilometers before any chance of reaching the event horizon itself. For smaller stellar mass black holes, the death by tidal forces happens even farther out. At 100 kilometers from a 5 solar mass black hole's event horizon, the tidal force between a person's head and feet would be approximately 3 million times the surface gravitational acceleration of Earth. There is no biological material or engineering material that withstands such forces. The stretching would begin gradually and then accelerate with terrifying speed. Your feet would accelerate faster than your torso. Your torso would accelerate faster than your head. The differential stretching would cause your body to elongate, your biological tissues reaching and then exceeding their tensile limits. As you crossed into the region of truly extreme tidal forces, the process would continue at the molecular level, then at the atomic level, your body disaggregating into a stream of elementary particles drawn into a thin thread along the direction of the gravitational gradient. For a supermassive black hole with the mass of Sagittarius A star, the story is completely different. Its tidal force at the event horizon is so weak that a person could cross it without any sensation at all. The tidal acceleration at the event horizon of Sagittarius A star, which has about 4.3 million solar masses, works out to roughly comparable to what you would experience standing on the surface of the Earth, which is to say, you feel nothing unusual from it whatsoever. You would not perceive any stretching. Your body would remain intact. For an even more massive black hole, the tidal forces at the event horizon are even gentler. A black hole with around 10 million solar masses or more would have tidal forces at its event horizon that are literally weaker than what you feel standing on Earth right now. The differential pull between your head and your feet due to the gradient in Earth's gravity, while tiny, actually exceeds the tidal force at the event horizon of such a massive black hole. a person crossing the event horizon of a billion solar mass black hole, a class that includes the M87 black hole and several others, would experience tidal forces so gentle at the moment of crossing that no biological signal of any kind would alert them to the transition. This distinction creates two fundamentally different stories about falling into a black hole, and which story applies depends entirely on the mass of the object doing the swallowing. For most of what follows, we will focus primarily on the experience of falling into a supermassive black hole, because it allows us to survive long enough to actually experience the journey in any meaningful sense. But the stellar mass case remains vivid and relevant, and we will return to it later. There is an additional wrinkle worth noting. Even for supermassive black holes where the tidal forces at the event horizon are gentle, the tidal forces increase as you fall deeper inside. The singularity, or whatever awaits at the endpoint of the journey, involves infinite curvature in the classical theory. So even if you survive the event horizon crossing undisturbed, the tidal forces will eventually grow to arbitrary strength as you approach the singularity. For the most massive black holes, spaghettification is delayed until well inside the event horizon, but it is not avoided. The forces that are gentle at the horizon become catastrophic somewhere on the inward journey, the exact point depending on the mass of the hole. For a billion solar mass black hole, the tidal forces might remain below lethal levels for a substantial fraction of the fall before escalating rapidly near the singularity. For Sagittarius A star, the tidal forces would become unbearable well before the singularity is reached, perhaps within seconds of the horizon crossing. The long approach. What you would see. The experience of approaching a black hole does not begin at the event horizon. It begins much farther out, in the region of space where the black hole's gravity has already begun to reshape the light arriving from the rest of the universe. At a great distance, you might see the black hole initially as an absence, a dark region in space surrounded by what looks like a distorted halo of light. The distortion arises because the black hole's gravity bends light passing near it, following the curves of space-time rather than traveling in straight lines through flat space. Light from stars and galaxies behind the black hole is bent around it, sometimes dramatically, producing multiple images of the same source, or in some cases, complete rings of light where a source lies precisely aligned. These are called Einstein rings, and they are a direct consequence of the gravitational lensing that general relativity predicts. The degree of distortion grows as you get closer and as the angular size of the black hole in your visual field increases. There is something worth sitting with here. The darkness you are looking at when you look toward a black hole is not empty space made dark by an absence of stars. It is a region where all the light that entered has been captured and cannot escape. The light that formerly passed through that region of space on its way to your eyes no longer does so. The blackness is informative rather than empty. It tells you precisely where the event horizon is, more or less, and by its shape and the distortion surrounding it, it encodes information about the geometry of space-time in that neighborhood. As you draw closer, the visual geometry begins to shift in ways that become increasingly hard to relate to ordinary experience. The dark region at the center, the shadow of the black hole, which is roughly twice the size of the event horizon itself, grows steadily in your visual field. But it does not grow the way a wall grows as you approach it. It grows faster on the sides than you might expect, as more and more of the light reaching your eyes from behind you is bent around the black hole and redirected toward you from increasingly extreme angles. Stars that should be behind you begin to appear at the periphery of your vision, their light bent on long curving paths around the singularity before arriving at your eyes from an unexpected direction. If you were to stop your approach at, say, 10 Schwarzschild radii from the event horizon and look around carefully, you would notice that the star field has already begun to distort significantly. Stars near the direction of the black hole have been displaced from their expected positions, their light bent around the dark center. More subtly, there would be a region behind the black hole where no stars appear, a shadow region surrounded by a brightened ring of gravitationally lensed starlight piled up from all directions behind the hole. This brightening near the edge of the shadow is not the accretion disk. It is purely gravitational lensing, present even for a completely isolated black hole with no matter falling into it. Surrounding the dark shadow, you would see the accretion disk if one exists. Not all black holes are actively accreting material. Sagittarius A star, for all its mass, is currently in a relatively quiet phase, slowly feeding from the stellar winds of a few dozen nearby stars. But when a black hole is actively consuming matter, drawing in gas, dust, or shredded stellar material, that material collects into a swirling, flattened structure called an accretion disk, and it glows. The friction between particles spiraling inward at different speeds heats the disk to temperatures that can reach tens of millions of degrees. The innermost edge of the accretion disk sits at what is called the innermost stable circular orbit, or ISCO, which for a non-rotating black hole lies exactly at 3 Schwarzschild radii, 3 times the event horizon radius. Inside this orbit, no stable circular paths exist, and matter at those distances rapidly plunges inward. The gas and plasma at the inner edge of the disk are moving at a substantial fraction of the speed of light. At these speeds, a relativistic effect called Doppler beaming makes the side of the disk rotating toward you appear dramatically brighter and bluer, while the receding side appears dimmer and shifted toward the red end of the spectrum. The asymmetry can be striking, one side blazing with compressed, energized light, the other side quieter and cooler in appearance. This asymmetry was captured in the real images of both the M87 black hole and Sagittarius A star, and matches predictions made decades before those images were taken. Light from the far side of the accretion disk, the part that would ordinarily be hidden behind the black hole, is bent over the top and bottom of the event horizon shadow by gravitational lensing, appearing as curved arcs of light both above and below the central darkness. When you look at such a system from the side, you see what looks like a disk that has split into humps, curving away from the shadow in multiple directions, each one a gravitationally bent image of some part of the disk that would otherwise be invisible to you. The overall appearance is something like a flattened orange or a ring that seems to wrap above and below the dark center, a configuration that was simulated in detail by astrophysicists years before the first black hole image was released, and which matched the actual images strikingly well. At a specific distance from the black hole, 1.5 times the Schwarzschild radius for a non-rotating black hole, lies the photon sphere. This is the boundary where gravity is strong enough to hold light in an unstable circular orbit. The orbit is unstable in the sense that a photon placed exactly there with exactly the right trajectory will orbit indefinitely in theory, but any slight perturbation will send it either spiraling outward to escape or inward to be swallowed. In practice, the photon sphere is not a surface you can sit on or interact with directly. Photons passing just outside this radius are deflected enough to curve significantly around the black hole before continuing outward. The result, as seen from the outside, is a bright and narrow ring of light close to the shadow boundary. This photon ring, as captured in the real images taken by the Event Horizon Telescope, is composed of nested rings of progressively decreasing brightness, light that has gone around the black hole once, twice, 3 times, each circuit adding another faint ring inside the previous one. In principle, infinitely many such rings exist, growing fainter and thinner and compressed toward the shadow edge. The brightest and most visible outer ring is what primarily appears in the EHT images. The subsequent inner rings are present but far below the detection threshold of current instruments. For a rotating black hole, the photon sphere becomes two separate photon orbits, an outer one for light traveling against the direction of rotation and an inner one for light traveling with it. These two photon orbits are separated by a finite distance that grows larger as the spin of the black hole increases. A maximally spinning black hole has inner and outer photon orbits separated most widely, and the shadow cast by such a black hole is slightly asymmetric compared to a non-rotating one. As you continue your approach, the star field visible above you, or rather behind you in the direction away from the black hole, occupies a shrinking cone. The black hole's shadow below you expands to fill a larger and larger fraction of your view. From the perspective of someone falling inward and looking outward, the view of the surrounding universe undergoes a progressive distortion. At a certain point along the approach, the entire sky visible to you begins to compress into a smaller and smaller region. Stars that were spread across a wide portion of the sky are concentrated toward the far side of your visual field, opposite the direction of your fall. The black hole below you expands to fill a growing fraction of your view. As you approach the photon sphere, the star field visible above you occupies only a narrow cone. Just at the photon sphere, a hovering observer, someone burning enormous amounts of fuel to maintain a fixed position rather than freely falling, would see the entire external universe compressed into a narrow ring, with the black hole's shadow filling essentially everything else. Each star in the universe would, in principle, be visible multiple times in that ring, because photons that have orbited the black hole any number of times before reaching the observer's eyes all arrive at slightly different angles, stacking images of the entire sky into that thin, bright band. A person hovering there would see, in a narrow strip of sky approximately perpendicular to their line of descent, simultaneously a star's direct image, its image from light that went once around the black hole, its image from light that went twice around, and so on, all layered into a single bright annular region. A freely falling observer, however, sees something different. The free-fall observer does not maintain a fixed position. They are in motion, and that motion affects the visual experience. For someone falling from rest at a very large distance, the outside universe remains visible over a larger angular region than a hovering observer would see at the same radius, because the motion of the fall shifts the observed directions of incoming light through a relativistic version of aberration. At the moment of crossing the event horizon, calculations suggest that the black hole's shadow subtends an angular radius of about 42 degrees from directly ahead, meaning the external universe is still visible in the remaining 138 degrees of the visual field. Nothing special happens to that view at the crossing point. There is no flash, no dramatic visual event. The event horizon is not a physical surface, it is a mathematical boundary, a surface of no return, but it has no local features distinguishing it from the space just outside it or just inside it, at least for a sufficiently large black hole where tidal forces are weak at that boundary. The view from outside. A frozen clock. Before following the falling traveler past the horizon, it is worth pausing to describe what someone watching from a safe distance would see. Because what the outside observer sees is almost entirely different from what the falling person experiences, and this divergence is one of the most striking consequences of general relativity in any everyday imaginable scenario. From a distant location, you watch a friend descend toward a supermassive black hole. At first, the fall proceeds as you might expect. Your friend accelerates, moving faster as gravity pulls them in. But then, something strange begins to happen. As your friend approaches the event horizon, their apparent motion begins to slow. Not because they are slowing down. From their own perspective, they continue accelerating. But the light they emit takes longer and longer to climb back out of the gravitational well to reach your eyes. The gravitational field near the event horizon is so strong that photons emitted outward are fighting against it with every meter of their escape. They lose energy to this fight. They slow down in terms of their rate of reception at your end, and their wavelength stretches in the process. The time between successive photons of light arriving from your friend grows. Each image you receive was emitted a little closer to the event horizon and has to fight a little harder to escape. In terms of the light reaching you, your friend appears to slow to a crawl, then to a near stop, and then to freeze, suspended just outside the event horizon like a photograph. Simultaneously, the light from your friend appears to stretch toward longer wavelengths. This is gravitational redshift, and it is distinct from the Doppler redshift caused by recession speed alone, though both effects are present here. What began as visible light redshifts to the infrared, then to microwave frequencies, then to radio wavelengths, as the photons lose more and more energy, fighting their way out of the deepening gravitational field. Your friend appears to grow dimmer and redder at the same time they appear to freeze, until they fade so completely below any conceivable detection threshold that, for all practical observational purposes, they vanish. The last photons they ever emitted while outside the horizon will travel toward you for effectively infinite coordinate time before reaching you. Stretched to such long wavelengths and carrying so little energy that no realistic detector could register them. They do not cross the event horizon as seen from your vantage point. From your perspective, no one and nothing ever quite crosses it. The event horizon, to the distant observer, is a surface at which time dilation becomes infinite, and all signals coming from a falling object are redshifted to zero energy. A calculation made for a solar mass black hole shows that the apparent luminosity of an infalling object fades away on a characteristic timescale of roughly 4 times its mass in appropriate units. For a solar mass black hole, that corresponds to about 20 microseconds of Schwarzschild coordinate time. After a few such timescales, the object's apparent luminosity has dropped by a factor of e to some very large power and is functionally invisible. For larger black holes, the timescale is proportionally longer, but the qualitative behavior is the same. There is an additional subtlety that took physicists years to fully appreciate. When an infalling observer emits a laser beam or a radio signal directed outward, back toward the distant observer, what does the distant observer receive? They receive the signals at an increasingly slow rate, each successive signal taking longer to arrive than the last. As the infalling observer approaches the event horizon, the signals received by the distant observer correspond to events happening ever closer to the horizon crossing, but each signal takes longer and longer to arrive. The total coordinate time for the observer to complete the crossing from the distant observer's reference frame is infinite. But this does not mean that the infalling observer takes an infinite amount of their own time to cross. Their personal experience, measured by their own heartbeat, their own clock, their own passage through the moments of their life, reaches the crossing in finite time and continues beyond it. This is the essential asymmetry: infinite coordinate time for the distant observer, finite proper time for the falling one. And general relativity says that proper time, the time registered by a physical clock carried along a world line, is the real, physical, invariant measure. Coordinate time is a bookkeeping convention, and the convention breaks down at the event horizon in a way that is physically significant only for the distant observer. This is a genuinely strange fact, and it took decades for physicists to fully disentangle it from the underlying physics. The key to understanding it without confusion is to recognize that the distant observer's experience describes only what that distant observer can see, which is constructed entirely from light signals received. It does not describe what is actually happening at and inside the event horizon, because that information cannot reach the distant observer by definition. The distant observer is describing their own reconstruction of events based on the light available to them, not the objective sequence of events in some universal timeline. General relativity replaced universal timelines with something more local, more perspectival, and in this case more startling. The German physicist Karl Schwarzschild, working from an exact solution of Einstein's field equations while stationed on the Eastern Front in 1916, derived the mathematical description of space-time around a non-rotating spherical mass. His solution contains a mathematical singularity at what we now call the Schwarzschild radius, the event horizon. For decades after his discovery, physicists debated whether this singularity was physical or merely a coordinate artifact. The answer, worked out conclusively by David Finkelstein in 1958, is that the singularity at the event horizon is entirely a coordinate artifact. It reflects a poor choice of coordinates, not a breakdown of the physics. In different coordinates, the event horizon is smooth and unremarkable. The coordinate singularity at the event horizon is analogous to the singularity that appears in polar coordinates at the north and south poles of the Earth. The poles are perfectly regular places, but the coordinate system breaks down there. The same is true of the event horizon in Schwarzschild coordinates. It is the coordinate system that has a problem, not space-time itself. This resolution took many years to fully establish and accept, partly because the new coordinates required to make the event horizon smooth involve mixing the concepts of space and time in ways that feel deeply uncomfortable. Working with those coordinates, it becomes mathematically transparent that the event horizon is simply a boundary, a one-way membrane, as physicist David Finkelstein described it, and that crossing it from the outside in is a smooth, continuous process from the infalling observer's perspective. The crossing, what the falling person experiences. From the perspective of the person falling in, the event horizon crossing is not detectable as a local event. This is one of the central and somewhat unsettling predictions of general relativity, and it has been confirmed through careful mathematical analysis of the geodesics, the curved paths through space-time, that a freely falling observer follows. Your own clocks tick normally, your heartbeat, your thoughts, your sense of time passing, all of these continue at the same rate they always have, at least from your own frame of reference. The ride may be smooth. The tidal forces for a large enough black hole may be imperceptible. There is no physical sign on your way down that reads, "You are now inside a black hole." The event horizon is a global property of space-time, defined relative to the entire future history of the universe outside, and it cannot be detected by a local measurement at the crossing point. This has a deceptively quiet but profound implication. You could, in principle, cross the event horizon of a supermassive black hole and not know it. You could spend an hour inside, looking around, continuing to observe the universe outside with the light that continues to stream past the horizon toward you, and have no local evidence that anything unusual has occurred. The laws of physics that you observe locally, the way objects fall, the speed of light, the behavior of electromagnetic radiation, remain entirely standard. The equivalence principle, which is one of the foundational ideas of general relativity, and states that free fall is locally indistinguishable from floating in empty space, far from any gravitational source, applies just as much inside the event horizon as outside it. There is no local frame that identifies the crossing. What changes is not local experience, but the causal structure of space-time around you. Once you have crossed the event horizon, every path that light can take through the space-time in front of you leads toward the singularity. The geometry of space-time has been warped so severely that all forward-pointing directions, all directions that correspond to moving toward the future rather than the past, curve inexorably toward the center. In ordinary space-time, you can choose to move in any direction of space while time moves forward. Inside the event horizon of a Schwarzschild black hole, the simplest non-rotating variety, the inward direction toward the singularity has become time-like. Moving toward the singularity is not like being pushed by a force you might in principle resist. It is more like being carried toward the future. You cannot resist the future. You cannot move backward in time any more than you can stop experiencing the passage of moments. The singularity is not a place in space you are falling toward. It is a moment in your personal future toward which every trajectory you can take is oriented. This realization that inside a black hole the singularity is future rather than directional is one of the features of black hole physics that most consistently surprises people encountering it for the first time. We think of a black hole as a deep hole in space with a dark center at the bottom. But that spatial intuition does not capture what general relativity actually says. Inside the event horizon, the coordinate that behaves like time is the one pointed toward the center. The singularity is not in the middle of a sphere you are falling through. It is in your future, and nothing you do can prevent reaching it. If you tried to fire a rocket engine to stop your fall after crossing the event horizon, you would only change the angle at which you approach the singularity, not your eventual arrival. The inward direction has become your time direction, and just as you cannot fire rockets to travel backward in time outside the black hole, you cannot fire rockets to travel outward inside it. The physics is exactly parallel. The best you could do is extend the amount of your own time remaining by choosing a path that takes the most gradual possible approach to the singularity. But the singularity remains in your future regardless. The time remaining between crossing the event horizon and reaching the singularity depends on the mass of the black hole. For a solar mass black hole, the time from horizon to singularity, measured in the falling observer's own proper time, is measured in microseconds. For a black hole with the mass of Sagittarius A star, around 4 million solar masses, the free fall time from the event horizon to the singularity is on the order of tens of seconds. For the M87 black hole with 6.5 billion solar masses, it extends to several hours. Even inside the most massive known black holes, the singularity is not infinitely far away in your personal future. While descending after crossing the event horizon, you would still be able to observe light from the external universe entering the black hole with you, because light from outside can travel inward past the horizon freely. It simply cannot travel outward. So your view does not go dark. You can still receive light. What changes is the direction it comes from, and increasingly the quality of what you can observe. Stars, galaxies, the cosmic microwave background, the faint thermal afterglow of the Big Bang, now stretched to microwave wavelengths. All of this radiation continues to reach you. The universe outside remains visible, but it becomes compressed into a progressively smaller angular region around the direction of the event horizon above you, which is now receding behind you as you fall inward. Your entire knowledge of the world outside is streaming in from a shrinking patch of sky. What would you observe looking back toward the event horizon from inside? In principle, you would see a dark circle around the direction you came from, surrounded by an increasingly compressed ring of the external universe. Light that entered the black hole before you did, light that was emitted by distant galaxies millions of years ago and has been traveling through the universe ever since, would arrive at your position, having passed the event horizon ahead of your own crossing. Light emitted after your crossing from the universe outside will follow you inward and can still reach you because light travels faster than you do even in curved space-time near the singularity. You can, in principle, receive signals from the outside universe until the moment you hit the singularity, though the signals arrive increasingly rapidly compressed. You would also, in principle, see time outside the black hole running increasingly fast from your perspective as you fall. The entire future of the external universe appears to you compressed and accelerated, though this effect has important nuances. The total amount of the external universe's future that you can observe between your horizon crossing and your singularity arrival is finite, not infinite, and it depends on the mass of the black hole. For very massive black holes with large interiors and long free-fall times, more of the external universe's future is in principle accessible to you before the singularity. For smaller black holes with short free-fall times, less external future fits into your remaining life. Either way, it is not a quiet experience in terms of information density. The spinning black hole, a different interior. The discussion so far has largely assumed the simplest kind of black hole, spherically symmetric, non-rotating, electrically neutral. In physics, this is described by the Schwarzschild metric, after Carl Schwarzschild's 1916 solution. It was the first exact solution to Einstein's field equations of general relativity ever found, remarkable for having been derived while the solver was stationed at the Eastern Front of a world war, working in the intervals between his military duties. Schwarzschild sent his solution to Einstein in December 1915, and Einstein presented it to the Prussian Academy of Sciences on his behalf in January 1916. Schwarzschild died of illness contracted at the front in May of that year, never knowing how consequential his calculation would become. But Schwarzschild black holes are idealizations. In reality, every object in the universe carries angular momentum. Stars rotate, gas clouds rotate. When a star collapses to form a black hole, it conserves that angular momentum, and the result is a rotating black hole. These are described by the Kerr metric, named after the New Zealand mathematician Roy Kerr, who found the solution in 1963. It took nearly half a century after the Schwarzschild solution to find the rotating case, which gives some indication of how much more mathematically complex the problem becomes when rotation is introduced. Many brilliant physicists, including people who had made landmark contributions to general relativity in other areas, attempted the problem and could not solve it. Kerr cracked it while working at the University of Texas, and the solution was presented at a conference in Dallas in 1963. By some accounts, the initial reception was muted, with many in the audience failing to appreciate the magnitude of what had just been found. Within a few years, the significance was universally recognized, and the Kerr metric has been the foundation for describing realistic astrophysical black holes ever since. A rotating black hole behaves differently from a non-rotating one in several significant ways. One of the most striking is a phenomenon called frame dragging, or the lens-Thirring effect. A rotating mass does not just curve space-time, it pulls and twists it, dragging it along in the direction of rotation the way a spinning ball drags the air around it. Near a rapidly rotating black hole, this dragging becomes so extreme that space-time itself is swept around in the direction of rotation. There is an outer boundary beyond the event horizon itself called the ergosphere, where the dragging of space-time is so powerful that no object, regardless of how powerful its engines or how much thrust it applies, can remain stationary relative to distant stars. Inside the ergosphere, everything is pulled around with the rotation of the black hole. To remain stationary in the ergosphere would require moving faster than light relative to the local frame, which is impossible. Any object inside the ergosphere must co-rotate with the black hole. The name ergosphere comes from the Greek word ergon, meaning work, and it reflects the fact that energy can, in principle, be extracted from this region. The ergosphere sits outside the event horizon at the equatorial regions and converges with it at the poles, touching the event horizon at the north and south poles of the rotation axis. Its shape is like a slightly flattened oblate spheroid that encloses the event horizon, bulging outward at the equator. Because it lies outside the event horizon, objects that enter it are not irretrievably lost. They can still escape to infinity if they have sufficient outward velocity. A remarkable process described by mathematician Roger Penrose in 1969, called the Penrose process, shows that it is theoretically possible to enter the ergosphere, extract energy from the rotational energy of the black hole, and escape with more energy than you entered with. The mechanism involves an object entering the ergosphere and splitting into two pieces. One piece is given a trajectory with negative energy relative to infinity, a concept that is possible only inside the ergosphere because of the frame dragging geometry, and falls into the black hole. The other piece escapes with more total energy than the original object carried coming in. The extra energy comes from the black hole's own rotation, slowing it slightly. The maximum energy extractable from a single such interaction is about 20.7% of the object's mass energy equivalent for a maximally rotating black hole. This process is considered a plausible mechanism behind some of the most energetic phenomena in the observable universe, including the relativistic jets of plasma that can extend for thousands of light years from the centers of active galaxies like M87. These jets carry enough energy to reshape the surrounding galaxy, suppressing star formation over regions millions of light years across, and the energy source is thought to be partly or wholly the rotational energy of the central spinning black hole. The interior structure of a rotating black hole is also more complex. Rather than a single event horizon and a single-point singularity, the Kerr geometry describes two separate event horizons, an outer and an inner one, and a singularity that is not a point but a ring, lying in the plane of rotation. The outer event horizon is analogous to the Schwarzschild event horizon, the boundary of no return for signals trying to reach the outside universe. The inner event horizon is a more exotic feature, a Cauchy horizon, a boundary beyond which the predictive power of the equations begins to break down. The ring singularity has some mathematically extraordinary properties. The equations describing the Kerr interior suggest that an object falling along the rotation axis could in principle pass through the center of the ring without hitting it, and emerge into a region of space-time on the other side with unusual properties. The mathematics of the fully extended Kerr space-time contains regions where closed, time-like curves exist, paths through space-time that loop back on themselves in time, though whether these represent genuine physical possibilities or are artifacts of the idealized exact solution is deeply contested. Most physicists believe the deep interior of a real rotating black hole would be substantially more chaotic than the clean mathematical solutions suggest, because even small perturbations from perfect symmetry appear to destabilize the idealized inner horizon structure into something far more turbulent and singular. What the singularity actually is. The singularity is one of the most commonly misrepresented concepts in popular discussions of black holes, and it is worth spending a moment with what physics actually says and does not say about it. In the Schwarzschild solution, the singularity at the center is a point of infinite density and infinite space-time curvature. The equations of general relativity produce quantities that become infinite there. But a singularity in a physical theory is not a description of something that actually exists. It is a signal that the theory has been pushed beyond its domain of validity. Infinite quantities in physics almost always mean that the model being used has broken down, not that nature itself has become infinite. The equations of general relativity are a description of gravity at large scales and relatively low energies. At the extreme densities and energies near a singularity, quantum mechanical effects become important in ways that general relativity simply does not account for. A complete theory of quantum gravity, which physicists do not currently have, though significant progress has been made in frameworks like string theory and loop quantum gravity, would presumably replace the infinite curvature singularity with something finite, even if still extremely exotic. What the singularity represents in the current theory, therefore, is not a literal infinitely dense point. It is the edge of the domain in which general relativity can make predictions. Beyond that edge, we genuinely do not know what happens. The singularity is where our map runs out and the territory becomes unknown. It is, in a specific technical sense, where space-time ends, at least in the classical description, and where a more complete theory would presumably need to take over. Roy Kerr himself, the discoverer of the rotating black hole solution, argued in recent years that the singularities predicted inside black holes may not be physically real even on their own terms, suggesting that they may be mathematical artifacts arising from the specific simplifying assumptions made in constructing the solutions rather than genuine physical predictions. This view is minority, but not fringe. The interior of a black hole beyond the event horizon is, by definition, causally disconnected from the rest of the universe and from any observation we could ever perform. This makes the physics of the interior both urgent as a theoretical puzzle and uniquely hard to constrain observationally. Hawking radiation and the information paradox. Stephen Hawking's most surprising contribution to black hole physics, published in 1974, was the demonstration that black holes are not perfectly black. They radiate. The mechanism involves quantum mechanics near the event horizon. In quantum field theory, the vacuum is not empty. Virtual particle-antiparticle pairs spontaneously appear and annihilate across the entire universe, constantly at every point in space. Most of these pairs annihilate before they can become real. But near the event horizon of a black hole, one member of a virtual pair can fall inward past the horizon before the annihilation can occur. The other member of the pair, having lost its partner to the black hole's interior, becomes a real particle and escapes to infinity. To a distant observer, this looks like radiation coming from the black hole. The energy for this radiation is extracted from the black hole itself, meaning the black hole slowly loses mass over time. This is Hawking radiation. Hawking radiation is fantastically weak for any black hole of astrophysical size. A black hole with the mass of our Sun would radiate at a temperature of approximately 60 nanokelvin, 60 billionths of a degree above absolute zero. The cosmic microwave background radiation filling the universe has a temperature of about 2.7 Kelvin, more than 45 million times hotter. So any astrophysical black hole is absorbing vastly more radiation from the background than it emits via Hawking radiation. Only extremely small black holes, if they exist, would radiate significantly. Such hypothetical micro-black holes would evaporate entirely in small fractions of a second. An astrophysical black hole the size of Sagittarius A star would take an unimaginably vast span of time to evaporate completely, far longer than the current age of the universe. But the theoretical significance of Hawking radiation goes far beyond the practical. It created a problem so deep and so persistent that it has been called the central open question in theoretical physics for the past half-century. The problem is called the black hole information paradox. Quantum mechanics is built on a principle called unitarity, which says that information is never truly destroyed in a physical process. If you know the complete quantum state of a system at one moment in time, you can, in principle, reconstruct what the state was at any earlier time and predict what it will be at any later time. Processes can scramble information beyond practical recovery, but they cannot annihilate it. The information is always there in principle, encoded somewhere in the quantum state of the world. Hawking showed, however, that the radiation a black hole emits appears to be purely thermal, characterized only by the black hole's mass, charge, and angular momentum, with no trace of the detailed quantum state of the matter that fell in to create it. If this is correct, then when a black hole finally evaporates away, the information about everything that fell in is gone. It is not scrambled and encoded somewhere. It is simply erased. This violates unitarity. It would mean that the combination of quantum mechanics and general relativity, the two most successful theories in the history of physics, produces an irreducible contradiction. Hawking initially argued that information is indeed lost and maintained this position for decades. Stephen Hawking famously made a bet with physicist John Preskill of Caltech, wagering that information is lost in black hole evaporation. In 2004, Hawking conceded the bet to Preskill, though his fellow wagerer Kip Thorne declined to concede, and the question is not fully settled even now. Most physicists today believe, based on work in string theory and related frameworks, that information is ultimately preserved rather than destroyed. But precisely how the information escapes from the black hole, encoded in subtle correlations in the Hawking radiation, remains unclear. The answer would likely require a complete theory of quantum gravity to state fully. One proposed resolution involves the firewall hypothesis put forward in 2012 by physicists Ahmed Almhairi, Donald Marolf, Joseph Polchinski, and James Sully. Their argument suggested that if information must be preserved in the outgoing Hawking radiation, and if the radiation must be entangled with the interior of the black hole in a way consistent with quantum mechanics, a fundamental principle called the monogamy of entanglement would be violated unless something dramatic happens at the event horizon. Their proposal was that the event horizon of a sufficiently old black hole would be replaced by a wall of high-energy radiation, a firewall, that would destroy any infalling observer at the boundary rather than allowing the smooth, locally unremarkable crossing that general relativity predicts. This would be a direct violation of Einstein's equivalence principle, which says that free-falling is locally indistinguishable from floating in empty space. The firewall debate exposed a genuine conflict between principles that physicists had long assumed were simultaneously valid: unitarity from quantum mechanics, the equivalence principle from general relativity, and the assumption that the physics at the event horizon is not dramatic from the infalling observer's point of view. At least one of these must give way, and physicists are not yet in agreement about which one. The question touches on the deepest level of what we know and do not know about how the universe operates. Two observers, one event. One of the quietest and most profound consequences of all this physics is the relationship between what the falling person experiences and what the outside observer records. From outside the black hole, the infalling traveler never quite crosses the event horizon. The light they emit redshifts to oblivion. Their image freezes and fades. From their own experience, they cross the event horizon in finite, proper time, continue inward, and reach the singularity. These are not two different accounts of the same event that can be reconciled by choosing the right frame. They are genuinely different experiences of two different observers in two different regions of space-time, connected by a boundary through which no information can pass. In general relativity, there is no universal present moment shared by all observers. Time is not a background against which events occur. It is a local property of a path through space-time. Two observers following different paths through the same region can measure different amounts of time between the same pair of events. This is not a measurement error or an illusion. It is how time actually works in a universe where gravity is the curvature of space-time. The outside observer, in a certain sense, never loses the infalling traveler. Their image remains frozen at the horizon, infinitely redshifted, infinitely dim, but in principle still there if you could build a detector sensitive enough to receive the last faint photons. The traveler from inside is beyond any causal contact with the outside universe. Messages they send cannot arrive outside. The light they emit bends back inward. They exist in a region of space-time that has been causally severed from the future history of the external world. A useful way to hold this without confusion is to think of space-time not as a stage on which events occur, but as a structure that encompasses all events at all times, with the causal connections between them encoded in the geometry. From this perspective, the event horizon is simply a surface in that structure where the causal connections run one way. Events inside can be caused by events outside, because signals from outside can travel inward. But events inside cannot cause events outside, because no signal can travel outward past the horizon. The horizon is therefore a one-way causal boundary in space-time, and the difference in experience between the two observers reflects this one-directional causal structure rather than any deep mystery about which account is really correct. Both accounts are correct in their respective causal regions. There is a subtlety here worth noting, and it has to do with the holographic principle, a conjecture developed in the 1990s primarily by theorists Gerard 't Hooft and Leonard Susskind. The holographic principle suggests that all the information about what happens inside a region of space can, in principle, be fully encoded on the boundary surface of that region. For a black hole, this means that the complete information about everything that has ever fallen in might be encoded on the event horizon surface. This does not mean the horizon is a physical wall. It means that the degrees of freedom of the interior can be fully described by degrees of freedom on the boundary, in the way that a three-dimensional room can in principle be fully described by information written on its two-dimensional walls. This remains a conjecture, not a proof, though it has received enormous support from work in theoretical physics, particularly from the correspondence between gravity in a certain kind of space-time and a specific type of quantum field theory living on that space-time's boundary, a framework called the ADS/CFT correspondence. What the holographic principle, if correct, would imply for our falling traveler is strange and not yet fully understood. If all the information about the traveler is encoded on the horizon surface at the moment of their crossing, then, in some sense, the distant observer does have access to all the information about what happened. It is written in the subtle correlations of the Hawking radiation emitted over the black hole's lifetime. The traveler's full quantum state, their memories, the precise arrangement of every atom in their body at the moment of crossing would, in principle, all be present in the radiation. Not accessible in any practical sense, but not destroyed. This is the sense in which most physicists today believe information is preserved rather than lost, even if the precise mechanism of that preservation remains one of the deepest open questions in physics. There is also a more practical and immediate sense in which the two-observer picture creates philosophical puzzles. If you are the falling observer and you know you have crossed the event horizon, you know that the distant observer watching you will never see you cross. You know that from their perspective you will be frozen just outside, fading slowly, for effectively forever. Meanwhile, you are continuing your journey inward, experiencing the passage of time, approaching the singularity. You exist in a present moment that, from the outside observer's perspective, corresponds to a moment that, in coordinate time, is infinitely in the future. Your personal present is their infinitely distant future, and yet you are experiencing it as now. This is one of the most visceral demonstrations that now is not a universal concept. Your now and their now are different moments in different regions of space-time, and there is no cosmic arbitrator to declare which one counts as the real present. The stellar mass journey, a different story. It is worth returning briefly to the stellar mass black hole scenario, because the physics there, while fatal, is in its own way vivid and illustrative. A stellar mass black hole with 5 times the mass of the Sun has a Schwarzschild radius of about 15 kilometers. If you approached one, you would be torn apart by tidal forces at a distance of roughly 700 kilometers, still far from the event horizon. The force at that distance between your head and your feet would already exceed the roughly 9,000 newtons that would pull a human body apart. The stretching would begin gradually and then accelerate with terrifying speed. Your feet would accelerate faster than your torso. Your torso would accelerate faster than your head. The differential stretching would cause your body to elongate, your biological tissues reaching and then exceeding their tensile limits. As you crossed into the region of truly extreme tidal forces, the process would continue at the molecular level, then at the atomic level, your body disaggregating into a stream of elementary particles drawn into a thin thread along the direction of the gravitational gradient. You would be drawn out from the bulk of matter that was once your body into a narrow filament. Spaghetti, in the now standard vocabulary, and that filament would continue to accelerate toward the event horizon, stretching thinner and thinner as it fell. Outside, a distant observer would see none of this in real time, because the light carrying this information is redshifted and delayed. The last photons emitted before crossing the event horizon would take effectively infinite time to escape, meaning the full collapse of any infalling object into the black hole is never directly visible from outside. What the distant observer might see, in systems where a stellar mass black hole is actively accreting matter from a companion star, is the glow of the accretion disk, X-rays and other high-energy radiation emitted by the superheated infalling gas, along with occasional flares and eruptions as magnetic instabilities rearrange the disk. The X-ray binaries studied by space telescopes provide observational evidence of black holes in this more active mode, even though the event horizon itself remains forever hidden. For a star unfortunate enough to stray too close to a supermassive black hole, the process is called a tidal disruption event. The tidal forces overwhelm the star's self-gravity, pulling it apart. and the resulting stream of stellar material spirals inward, forming a temporary accretion disk and producing a flare of radiation that can outshine the entire host galaxy for months. In October 2019, researchers identified one of the closest such events ever detected in a spiral galaxy within the Andromeda constellation. The star, similar in mass to our Sun, was torn apart by a supermassive black hole, and unusually, most of the material was not immediately swallowed but was ejected outward, creating a new puzzle about how black holes process disrupted material. These tidal disruption events are valuable to astronomers precisely because they briefly illuminate black holes that would otherwise be quiescent and undetectable. They are the black hole announcing itself through an act of destruction, one of the few signals it is capable of sending. The contrast between the stellar mass and supermassive experiences is instructive for understanding what the event horizon represents in terms of physical scale. For a stellar mass black hole, the event horizon is a tiny object, a sphere only about 30 kilometers across for a 10 solar mass black hole. For the M87 black hole, the interior geometry encompasses a region larger than our solar system, and the freefall time from the horizon to the singularity spans hours. The scale difference is difficult to hold in the mind simultaneously. Both are black holes in the same physical sense. The underlying physics is identical. The experiential and geometric scales are incomparably different. The deepest uncertainty. There is a moment, or more accurately a region, that physics cannot currently describe with any confidence. It is the end point of the journey, the singularity, or whatever replaces it in a more complete theory of physics. Inside a non-rotating Schwarzschild black hole, general relativity predicts that space-time curvature grows without limit as the singularity is approached. Any perturbations introduced by infalling matter, the inevitable asymmetries of real objects in real situations, would cause the tidal forces to oscillate chaotically and intensify. The matter forming the infalling body would be compressed into progressively smaller volumes while being subjected to rapidly changing directions of extreme tidal stress. The physical experience, if any observer could survive to have one, would involve tidal forces that are not only immense but directionless in any fixed sense, oscillating as the space-time geometry churns. Every molecular bond would be broken. Every atomic structure would be disrupted. The endpoint in the classical theory is compression into an infinitely small point of infinite density. For a rotating black hole, the inner geometry is more complex and less stable. Perturbations appear to destabilize the idealized Kerr interior into something more chaotic near the inner horizon. The eventual state of infalling matter in a real rotating black hole is not definitively known even within classical general relativity, and the role of quantum effects at extreme densities adds further uncertainty. What is consistent across all scenarios is that once inside the event horizon, there is no return. No force, no technology, no trajectory can take you back out. The inward direction is the temporal direction, and you cannot travel backward in time. The singularity, or whatever the end point of the journey actually is in a complete theory, will be reached in finite proper time. The question of what actually happens at those extreme densities, and whether the singularity is replaced by something else in a quantum theory of gravity, is one of the genuinely open questions in fundamental physics. Some approaches in loop quantum gravity suggest a quantum bounce, in which the collapsing matter reaches extremely high but finite density and then rebounds, potentially creating a new region of expanding space-time that is causally inaccessible from both the original infalling matter's perspective and from outside the original black hole. String theory approaches tend to emphasize the holographic principle and the encoding of interior information on the horizon surface without necessarily making a specific claim about what replaces the singularity geometrically. Other approaches suggest that quantum effects spread out the singularity into a region of extreme but finite curvature at the Planck scale, where the smooth geometry of space-time gives way to something more granular and probabilistic. None of these approaches has produced a definitive, experimentally tested answer. The physics at the Planck scale, the scale at which quantum effects become relevant for gravity, corresponding to lengths of about 1.6 times 10 to the negative 35 meters, is a frontier beyond which our current toolkit does not reach. It is a question that is formally unanswerable from outside, because the answer is locked inside a causal horizon that cannot be breached. The universe keeps its deepest secret behind a door it wrote into the laws of physics themselves. Not a door that might eventually be opened with better technology. A door that the structure of causality itself seals permanently from the perspective of any observer who remains outside. What all of this reveals about space and time. The journey into a black hole, even conducted entirely in thought, is not merely an exercise in exotic physics. It reveals something important about the nature of the universe at a fundamental level. Gravity is not a force in the ordinary sense. It is the curvature of space-time, and matter moving through curved space-time simply follows the straightest possible path through that curved geometry. On large scales and in weak fields, those paths are what Newtonian mechanics calls falling. In extreme fields, near black holes, the curvature becomes so severe that paths through space-time which were available to you in flat space simply no longer exist. You cannot travel outward from inside the event horizon for the same reason you cannot travel into your own past. Those paths do not exist in the space-time you occupy. This insight, that gravity is geometry rather than force, was one of the most radical conceptual shifts in the history of science. Newton described gravity as a force acting across a distance, instantaneously pulling objects toward each other through empty space. Einstein replaced this with a picture in which massive objects curve the space-time around them, and other objects simply follow the natural curves of that geometry. The sun does not pull the Earth. The sun curves the space-time around it, and the Earth follows the natural curved path through that geometry, which we experience as an orbit. This is not merely a different mathematical description of the same thing. It makes genuinely different predictions, and those predictions have been tested with extraordinary precision. The bending of light around massive objects, the existence of gravitational waves, gravitational time dilation, and the existence of black holes themselves are all predictions of this geometric picture of gravity that have been confirmed observationally. Time itself is not universal. Two clocks in different gravitational fields run at different rates. Two observers following different paths through space-time will measure different amounts of time between the same pair of events. This is not perception or psychology. It is geometry. The universe does not have a single master clock ticking out universal seconds that everyone experiences equally. It has a local structure, and the rate at which your clock ticks depends on where you are and how you are moving. This is strange, and it is verified. GPS satellites must account for time dilation from both their velocity and their distance from Earth's gravitational field in order to provide accurate positioning data. Without these corrections, GPS errors would accumulate at a rate of roughly 10 kilometers per day. The clocks on GPS satellites run fast by about 45 microseconds per day due to being higher in Earth's gravitational field, and slow by about 7 microseconds per day due to their orbital velocity. The net effect is about 38 microseconds per day, which corresponds to position errors of roughly 11 kilometers per day without correction. The technology you carry in your pocket relies on accounting for the distortion of time by gravity and motion. Near a black hole, these effects become extreme rather than subtle. A clock hovering just outside the event horizon of any black hole, expending enormous amounts of energy to maintain its position against the gravitational pull, would run at a rate approaching zero compared to a clock far from the black hole. A clock falling freely through the event horizon would, from the perspective of the distant clock, appear to slow down and stop, not gradually and smoothly, but increasingly rapidly, freezing asymptotically as it approaches the horizon. From the perspective of the falling clock, nothing unusual happens. It continues ticking normally as it crosses the boundary that the distant observer will never see it cross. The difference in experience between the infalling observer and the distant observer is not a paradox or an inconsistency. It is a consequence of the fact that there is no cosmic vantage point from which all events can be arranged into a single, coherent timeline. General relativity replaces the absolute time of Newtonian mechanics with local proper times, path-dependent and frame-specific. Each observer carries their own clock and their own experience of the sequence of events. This is the universe operating as it actually is, not as human intuition evolved on the surface of a planet where gravitational time dilation is immeasurably small, was equipped to expect. The information paradox points towards something even deeper, the possibility that we are missing a layer of reality. Quantum mechanics and general relativity are both spectacularly successful theories in their domains, tested to extraordinary precision. They also appear to be fundamentally incompatible with each other in certain extreme regimes, of which the interior of a black hole is the most dramatic example. The resolution of this incompatibility, a theory of quantum gravity, would likely change our understanding of space, time, information, and possibly the nature of matter at the most fundamental level we can currently conceive of. What lies beyond the singularity is not merely an open question about black holes. It may be the question that, when answered, reveals the next layer of how the universe is constructed. It is also worth noticing that black holes are not purely theoretical constructs or distant curiosities. They are among the most common massive objects in the universe. Every large galaxy hosts a supermassive black hole at its center. Stellar mass black holes number in the tens of millions within the Milky Way alone, most of them dark and quiet, detectable only through their gravitational effects on neighboring stars or the occasional accretion of gas. The merger of two black holes produces gravitational waves that have now been detected dozens of times by the LIGO and Virgo detectors. Ripples in space-time geometry propagating at the speed of light across billions of light years before arriving at Earth and stretching our most precise instruments by a fraction of the diameter of a proton. Black holes are not curiosities at the edge of physics. They are woven into the large-scale structure of the universe. They regulate galaxy growth. They shape the distribution of stars. They anchor entire galactic ecosystems of millions of orbiting objects. They are, in a very real sense, some of the most consequential objects in the universe, even though nothing that enters them can ever return to tell us what they are like inside. There is a final thought worth holding as we come to the end of this journey. The event horizon is the ultimate limit on knowledge. Not the limit of what we have currently figured out. Not the limit of what sufficiently advanced technology might someday tell us. It is the limit written into the causal structure of the universe itself, as fundamental as the speed of light, as unbreakable as the second law of thermodynamics. The laws of physics themselves have drawn a line, and beyond that line, inside that horizon, no message can ever travel to tell us what is there. The universe contains secrets that it has placed behind a door that physics itself locks and keeps locked forever, at least from the perspective of anyone outside. That is an extraordinary thing to sit with. Not frustrating exactly, more like humbling, more like the feeling of standing at the edge of a continent you cannot cross and knowing that the other side of the ocean is real, even if you can never visit it and no ship can return from it to describe what it found. The singularity of observation. There is a distinction that does not always get made clearly in popular accounts of black holes, and it is worth making here. There is a difference between what we have actually observed and measured and what we infer from theory about regions we cannot observe. On the observational side, the evidence for black holes is now extraordinarily robust. The first gravitational wave detection by the Laser Interferometer Gravitational Wave Observatory, reported in February 2016, recorded the merger of two stellar mass black holes, roughly 1.3 billion light-years from Earth. The signal matched theoretical predictions in its frequency, duration, and amplitude with remarkable precision. Since then, dozens of such mergers have been detected, including collisions between two black holes, two neutron stars, and mixed pairs. Each event is a window into the behavior of space-time under the most extreme conditions achievable in the observable universe, and each one has confirmed general relativity's predictions at a level that continues to impress physicists who work on alternative theories. The Event Horizon Telescope, images of M87's black hole in 2019 and Sagittarius A star in 2022 provided the first direct visual confirmation of the event horizon shadow, the dark region that forms because all light within the horizon is captured and light near the horizon is strongly deflected. The size and shape of that shadow were predicted by general relativity decades before the images were made. The images matched. This is not a trivial match. The predictions depend on the full machinery of general relativity and the strong field regime, and any substantial deviation from the theory would have produced a measurably different shadow size or shape. No deviation was found. What we have not observed, and by definition cannot observe from outside, is the interior. Everything we say about the inside of the event horizon, the behavior of space-time after the crossing, the approach to the singularity, the nature of the singularity itself, comes from mathematical extrapolation of the equations. Those equations have been tested extensively in the exterior regime. We have every reason to trust them there. But the interior is a region causally disconnected from any measurement we could perform, and the question of whether the mathematical extrapolation into the interior accurately describes physical reality is not directly testable from outside. It is constrained by the exterior observations because changes to the theory that affected the interior would generally also affect the exterior and produce measurable differences. But the constraints are indirect, and the deepest questions about what happens near the singularity involve regimes where quantum effects become important and where we know the classical theory is incomplete. Holding this distinction in mind does not weaken the story, it makes it more honest. We have measured the shadow of a black hole. We have heard two black holes collide over 1 billion years ago. We have watched stars orbit an invisible 4 million solar mass object at the center of our galaxy for 25 years. We have done all of this without being able to ask what it is like inside. And that combination, extraordinary precision about the exterior, complete epistemic closure about the interior, is what makes black holes genuinely unlike anything else in the observable universe. The numbers worth holding. Before leaving this topic, it is worth gathering some of the specific numbers that give this subject its scale and grounding. Numbers in astrophysics often seem abstract, but in this context they carry the weight of real geography, the geography of space-time and gravity, and the outcomes they produce. Sagittarius A star, the supermassive black hole at the center of the Milky Way, lies approximately 26,000 light-years from our solar system. That distance is so large that the light we observe from the region around it left before the last ice age ended on Earth. Its mass of about 4.3 million solar masses is contained within a Schwarzschild radius of roughly 12 million kilometers, or about 0.08 astronomical units, smaller than the distance from the Sun to Mercury, which averages about 0.39 astronomical units. The object's mass is therefore 4.3 million suns compressed into a sphere that fits comfortably between the Sun and its innermost planet. The star S2, one of the many stars orbiting the galactic center, completes one orbit of Sagittarius A star in approximately 15.9 years, reaching a maximum speed during its closest approach of about 7,650 kilometers per second, roughly 2.5% of the speed of light. At that speed, S2 could travel from the Earth to the Moon in less than a second. It is the tracking of S2 and other S-stars by infrared telescopes over decades that provided the first definitive evidence that the object at the galactic center is a supermassive black hole. Reinhard Genzel and Andrea Ghez, who led the two independent teams that conducted this tracking, shared the 2020 Nobel Prize in Physics for this work. The M87 black hole, the first to be directly imaged, has a mass of approximately 6.5 billion solar masses. Its event horizon has a Schwarzschild radius of roughly 19 billion kilometers, or about 120 astronomical units, larger than the orbit of Pluto, which averages about 39 astronomical units from the Sun. Light crossing the shadow of the M87 black hole's event horizon, a shadow roughly twice the size of the horizon itself, would take about 2.5 days. The M87 black hole also drives a relativistic jet of plasma that extends at least 5,000 light-years from the galaxy's center, one of the most powerful and sustained jets in any nearby galaxy, visible across a wide range of wavelengths from radio to gamma rays. For a person falling into a supermassive black hole with the mass of Sagittarius A star, assuming they begin their fall from rest at a very large distance and assuming no tidal disruption occurs, the free fall time from the event horizon to the singularity, measured on their own clock, would be on the order of seconds to tens of seconds. For the M87 black hole, that same journey from the event horizon inward would take, by the infalling observer's own clocks, somewhere on the order of hours. For the most massive known black holes, approaching 66 billion solar masses like TON 618, the freefall time from horizon to singularity could span days. A stellar mass black hole with 5 solar masses has an event horizon radius of about 15 kilometers. A person would be killed by tidal forces at a distance of approximately 700 kilometers from that horizon, with the tidal acceleration between their head and feet reaching roughly 100 times the gravitational acceleration at Earth's surface at that distance. At 100 kilometers from such a horizon, the tidal acceleration would be more than 3 million times the surface gravity of Earth. For context, trained fighter pilots lose consciousness at around 9 times the surface gravity of Earth from blood draining from the brain. 3 million times that is not a number that maps to any biological experience. It is simply obliteration. The temperature of Hawking radiation from a solar mass black hole is approximately 60 nanokelvin, 60 billionths of a degree above absolute zero. The time for such a black hole to completely evaporate via Hawking radiation, assuming no accretion, would be on the order of 2 × 10⁻�67 years, an enormous multiple of the current age of the universe, which is approximately 13.8 billion years. To put the evaporation timescale in perspective, the current age of the universe is about 10 billion years. The evaporation time of a solar mass black hole is 10 to the 57th power times that age. There is no comparison in ordinary experience that conveys this number. It is simply a measure of how completely irrelevant Hawking evaporation is for any black hole of astrophysical size over any timescale that astronomical observation could possibly address. The innermost stable circular orbit around a non-rotating black hole lies at exactly 3 Schwarzschild radii, 3 times the event horizon radius. For a stellar mass black hole of 5 solar masses with a Schwarzschild radius of 15 kilometers, this orbit lies at 45 kilometers from the singularity. Material at this orbit moves at approximately half the speed of light. For a rotating black hole, the innermost stable orbit depends on the spin and can shrink to as close as the event horizon itself for a maximally spinning black hole, allowing orbiting material to remain stable much closer in and extract more energy from the gravitational field before plunging inward. The quiet strangeness of all of this. It would be easy to let the mathematics and the scales of this subject crowd out the quiet strangeness of what is actually being described. So it is worth pausing one last time to sit with what these ideas really mean. A black hole is a region where the structure of space-time has been reshaped so profoundly that the direction we call moving forward in time and the direction we call falling inward have become, inside the event horizon, the same thing. The singularity is not in front of you, below you, or anywhere in any spatial direction. It is in your future, as inevitable as tomorrow. The boundary between outside and inside, the event horizon, is not a place you can point to from outside, not a wall, not a surface with any local features. It is a horizon in the most precise sense. The limit of what can reach you from certain regions, invisible from the inside, infinitely relevant from the outside. You cross it without any local sign. Your personal experience continues uninterrupted, and yet the universe you came from has, from the standpoint of your causal future, been permanently left behind. The outside observer watches you freeze and fade. You, falling, watch the universe outside accelerate and compress. Neither of you is wrong, neither view is an illusion. They are both accurate accounts of what happens in your respective regions of space-time, connected to each other by the physics of light and gravity and the fundamental structure of a universe that does not have a single master clock and does not guarantee that all observers share the same experience of any given event. And at the end of the journey, in a region where our best theories stop making predictions we trust, there is the singularity, or whatever is there instead. Something the universe has chosen with mathematical precision to place behind a horizon through which no information can ever return. The deepest answer physics currently has to the question of what happens there is, we do not know. That is not an admission of failure. It is an honest statement of where we are, and it is the kind of honest statement that has historically preceded the most significant advances in our understanding of how the universe works. There is something worth reflecting on about the position we are in as observers of black holes. We have photographed the shadow of an object from which no light escapes. We have listened to the ripples in space-time created when 2 such objects collided 1 billion light-years away, and registered the resulting tremor in detectors sensitive enough to measure a displacement smaller than 1/10,000th the width of a proton. We have tracked the orbits of stars circling an invisible object at the center of our own galaxy for over 20 years and measured its mass to within a fraction of a percent. We have done all of this without sending anything into a black hole, without receiving any information from inside one, without ever having any direct access to the interior. This is one of the most extraordinary things about science. The accumulation of indirect evidence can be so precise and so comprehensive that we can be confident about properties of objects we can never directly examine. The physics of black holes is not speculative in the way that it once was. The general relativistic description has passed every observational test we have been able to construct. The event horizon is real. The time dilation is real. The gravitational redshift is real. The shadow in the Event Horizon Telescope images is exactly the size and shape that general relativity predicts. The gravitational wave signals from merging black holes match the predictions of numerical relativity to precision that still impresses the people who work on it. What remains unknown is the interior, not because the exterior physics is uncertain, but because causality itself prevents the information from reaching us. There are black holes in the universe right now, billions of them, quietly sitting in the centers of galaxies, slowly evaporating on time scales longer than the current age of the universe, accreting occasional wisps of gas and dust, bending the light of everything behind them, holding their secrets behind horizons that the laws of physics themselves enforce. They are not strange additions to an otherwise orderly universe. They are what happens when gravity, time, and the geometry of space-time are taken to their logical extremes. They are where the ordinary becomes extraordinary and where the extraordinary becomes, for now, unknowable. And somewhere in the universe right now, there is a particle of infalling matter crossing an event horizon, experiencing nothing unusual at that moment, heading toward a future it cannot escape, in a space-time region that will never communicate with the rest of the universe again. That particle carries no information about what is ahead of it, just like us. If this calm journey into one of the universe's most extreme environments was worth your time tonight, a like on this video helps others find it. And subscribing to the Sleepy Universe means more quiet explorations of big science are headed your way. Leave a comment and let us know what you would want to know if you were the one falling in. The physics is strange enough that almost any question leads somewhere worth going. Sleep well. The universe will still be here when you wake up.